All right, so we're going to learn about t-tests, and t-tests are the tests you're supposed to use when you're comparing two means to make an inference about two population means. Like I just said, when you use a t-test, you're using it to compare two population means, or comparing two means to make an inference about two population means. So you use the ANOVA when you're comparing three or more means, and you use the t-test when you are comparing two means. The t-test in concept is identical to the ANOVA in concept. It is calculated a little differently by hand, but I do want you to know that mathematically, a t squared, your t statistic squared, equals your f statistic. So these are the same thing. So everything that's happening in your f statistic, you can also view as happening conceptually in your t statistic. So it's the variation among your sample means divided by your variation within your sample means. The actual formula is mean difference divided by average variation within your conditions, which is known as standard error. So your t statistic is calculated by taking your mean difference divided by your standard error. And while this doesn't really matter to you, your standard error is a standard deviation in the made-up distribution where we assume the null is true. So when someone's saying standard error, that is simply the standard deviation in that made-up distribution that we made ourselves. Remember, we said it was a normal curve. Well, it's actually a t-distribution. The standard deviation inside that distribution of sample means from the predicted, or sample mean differences from the predicted mean difference of 0. That is your standard error. You don't have to know that. I'm just telling you that. I'll never test you on that. What does matter? Your null hypothesis is that your population mean difference is 0. I'm going to state it this way. You're going to see other people state it as mean of group 1. The population mean of group 1 equals the population mean of group 2. I like to simplify stuff. We're not comparing two different distributions. We're looking at a distribution of mean differences like we did in class when we introduced p-value. Your p-value means the same thing as it always has. The probability of sampling data, like my data, if the null were false, p less than 0.05, the population mean difference is not 0. That's what I know. If p is greater than 0.05, I still know nothing. We are making inferences about population mean differences. If p is less than 0.05, we know that the population mean difference is not 0. If p is greater than 0.05, I know nothing. The other thing that matters is effect size. So the main effect size when you're comparing two groups is called a Cohen's d. It is a very simple effect size. It's a mean difference divided by the average standard deviation. So you take, your standard deviation group 1 and your standard deviation group 2 and you average those together. Now, there are different ways to average them together. There's a pooled average and other things like that. So if you see that, don't be confused. Nonetheless, the ideas are very, very simple. So what it's doing is converting your mean difference to a standard deviation difference. So let's say you had a mean difference in 100 units. Your average standard deviation was 200 units. Your Cohen's d takes that 100 divided by that 200 to get a Cohen's d of 0.5, so that your mean difference is actually half a standard deviation difference. That's all that's going on here. Your mean difference of 100 is really a mean difference of half a standard deviation. And ultimately, this allows us to compare studies across different types of measures and different studies and so forth. Now, the Cohen's d does have a very simple interpretation. 0.2 is small, 0.5 is medium, 0.8 is large. Small is a small effect. 0.5 is the average effect in our field, and 0.8 is large. All right, so how do we put effect size and p-values together? So first, when your p-value is greater than 0.05, you still know nothing. That'll make sense as we go through the lecture, but essentially, when your p-value is greater than 0.05, we have to realize that, the null could be true, the null could be false, we could do bad science. Whenever there's an indicator that bad science could be at play, we can't trust it. So p greater than 0.05 is an indicator that we can't trust our own science. And that's something that we forget. So it doesn't matter if it's small, medium, large, or less than small. P greater than 0.05, you still know nothing. Now, when P is less than 0.05, we got to put this in perspective. What do we know? We know that, that the null hypothesis is likely false, so much so that we're betting against it and saying it is false. We know that there's a probability it is true, but we're just going to ignore that for now, right? But if we assume that the null hypothesis is wrong, in this case, we're saying that our mean difference is not zero. But our mean difference could be tiny. It could be 0.00001, or it could be massive, 1,000,000,000%. Who knows? Well, so ultimately, if we're in this situation and we find that we have an effect that's less than small, a Cohen's d that's less than 0.2, the null is not true, but your effect is too weak to matter. That's basically the point where you did good science, but the effect is not practically important. When we move to small, medium, and large, it's a little bit more difficult to make the same claim. But if we have a small effect, what we know there is that the null hypothesis is not true, but the effect, it's not going to make the greatest change in the world. A medium effect is the average effect in our field, and a large effect is amazing discovery. So it's really in those small and less than small cases that we have to be careful. For example, I'll give you an example that's not psychology. Let's say our P was less than 0.05, and this was for a vaccine, and the effectiveness of the vaccine was 5%. It's not zero. The true population mean difference, those who got the vaccine and those who did not, is not zero, but it's not an effect that matters. We want vaccines to have large effect size and significant results. The significance tells you if the study was done well, that we can trust it, that the experimenters were competent, but the effect size tells us how much that effect matters. Now, a lot of folks recognize that the p-value statistics aren't the only way to do it. What is happening in our fields is that folks are starting to use 95% confidence intervals of effect sizes like Cohen's d to replace p-value statistics. The math is kind of complicated. I'm not going to talk about the formulas because computers can do it. But essentially, what's a 95% confidence interval of a Cohen's d? So your sampled Cohen's d is the middle of a normal curve. You look at the middle 95% of this normal curve that is centered around your sampled Cohen's d. And what we know, that's our 95% confidence interval. And what we know is that 95% of the time, 95% confidence intervals contain the true population's Cohen's d. So let's just look at this in action. So we got a 95% confidence interval. They can tell us if the null is true. Right before our p is greater than 0.05, we know nothing. Well, if you add a confidence interval to this, and your 95% confidence interval of Cohen's d falls between a less than small effect and a less than small effect, a negative 0.19 and a positive 0.19, what do you know? You know that essentially the null is true. This effect doesn't matter, right? Worst case scenario, the effect is smaller than small. Best case scenario, the effect is smaller than small in the opposite direction. The effect is smaller than small. Heck, that sounds like the null is true to me, right? That's why I like the 95% confidence intervals. For this case, when you do good science and the null is true, you can actually start to kind of make an argument that the null is true. 95% confidence intervals of Cohen's d can tell you how awesome your study is. Remember, p-values just tell you if the null hypothesis is false, or we're going to bet against that null hypothesis, right? But if we have a 95% confidence interval of Cohen's d, and we know that 95% of 95% confidence intervals contain the true population's Cohen's d, we can say a little bit more. In this case, we are 95% confident that the true effect that we're interested in lies between a large and a massive effect. This is amazing. The study is amazing. The work is amazing. We know this is a large effect. This is a great, we can really say that. Where with just our p-values, all we know is that the population mean difference is not zero. Here we're saying we know the population mean difference is a large effect. So that's pretty cool. 95% confidence intervals of Cohen's d can tell you how crappy your study is. So if we look at this, we got a 95% confidence interval of Cohen's d that goes from a -1 to a +1. All right, that's basically every effect that exists on the planet. A large effect in one direction to a large effect in another direction. It could be anything in between those. Could be a large effect in the negative direction, a medium effect in the negative direction, a small effect in the negative direction, a less than small effect in the negative direction, a null effect, a small effect in the positive direction, a medium effect, a large effect in the positive direction. We literally know nothing. Right? If you look at this, we just literally know nothing here. You will often find confidence intervals like this when your p-value is greater than 0.05. It basically always works out like this, to where you literally know nothing. So 95% confidence intervals, how do you use them? I use them in my own research. It's not standard practice yet. You don't have to do it, but ultimately, when you're using these intervals, you understand that inside the interval, anywhere inside the interval, the true population Cohen's d could exist, and so we have to be conservative. For example, take the first interval that suggests that the true population's Cohen's d could be anything from a medium effect to a large effect. We have to assume it's a medium effect. It's not the end of the world, but we can't say this is a large effect, right? Like, scientists are conservative. That's what you're learning with the p-values. The same holds true for 95% confidence intervals. Now we go into the next 95% confidence interval of Cohen's d. We learn that the effect could be so less than small that it's super, super tiny to a massive effect. What do we learn there? Well, the true population effect size could be less than small. That's the conservative interpretation. We've learned we have to do better research. The next example is really interesting. So negative signs in the Cohen's d. Negative means it goes in the opposite direction from the positive, and you'll see that in the homework. But ultimately, this one could be anything from an effect that is super large in one direction to an effect that is super large in the opposite direction, and everything in between. In this case, I know nothing. The conservative estimate is I know nothing. Not that the two means are the same. Now, the final example is one of my favorite examples. 95% confidence interval of Cohen's d is from less than small to less than small. In this case, right, less than small in the negative direction, less than small in the positive direction. The true population value is going to lie between there. So worst case scenario, it's a less than small effect in one direction. Best case scenario, it's a less than small effect in the other direction. What do we know? It's a less than small effect. It's basically zero. I'm going to argue the null hypothesis is practically true. And those are the advantages of 95% confidence intervals. So we have 3 different t-tests that you need to use. The first one is the one sample t-test, and you use this when you argue that you know one population mean before you ever ran your data. Now, this is often going to be something like massive national data, like the average SAT score, something like that. It's very uncommon to use the one sample t-test in real life, but it's something that we're expected to teach you. The second one is your independent samples t-test. This is for between subjects designs. So between subjects designs, you have people randomly assigned to groups, or you have people naturally assigned to one of 2 groups, and that is an independent samples design. For the dependent samples design, this is the dependent samples t-test, also known as the paired samples t-test, also known as the repeated measures t-test. 3 names there. Okay, don't let them fool you. Is a within subjects design. So every participant participates in every condition. That's one way you can get it. In twin studies, you randomly assign twins to a condition. Technically, you use a dependent samples t-test to analyze that data because data from twin 1 are linked to data from twin 2. In a matched pairs design, where you pretest people on something like anxiety, right? And you have pairs of people that have the same level of anxiety before the experiment, like you would also use a dependent samples t-test because those data are linked to those pre-selected test scores. But essentially, for the most part, it's between subjects designs and within subjects designs that determine which test you use. T-test. This is a special case, okay? I think it's a bad statistic. I don't think we should use it, but I got to teach it to you. We know that the population, the average SAT score in the population is 1,000, even though the entire population of humans and Americans have not taken the SAT. So I'm just going to leave that there. That's my gripe with it, okay? But we're going to assume that we actually know the population. I'm just going to let it ride, okay? So I then want to test the hypothesis that me and my cousins are smarter than the national average. I'm just having fun. I don't even have that many cousins. I don't have that many cousins. So I'm just having fun with this test here. So I have data. I have 1100, I have 1600, 800, and all that. I'm going to enter this into Jamovi. I'm just going to call it Derwicky's SATs, right? That's what it represents. It's a continuous variable. I'm going to go ahead and put this in there. 1000. And you can see the 5 steps. They're not going to change. I'm not going to talk about them anymore. 1600. 800, 1010, 900, 1100, 700, and 1500. I'm going to, I just wanted to hide that. I'm going to click t-test. What am I going to do? I'm going to do the one sample t-test. The first thing that you will forget is to change your test value. So change your test value to 1000. That's test value is the known population mean. Okay. I am going to put in the Derwicky SAT scores. Oh, I'm going to just do everything I'm supposed to do, then show you the output because it's blocking me, but that's okay. The effect size, which is your Cohen's d, I want my 95% confidence interval of that. You can ignore that part. Also, I want my descriptives and my descriptives plot. Now that gets me my descriptive statistics. A lot easier with the t-test than with ANOVA. I acknowledge that. My descriptive plots, you can see I get a plot over here. I'll go through all that in a second. So I got my plot. And up here I have my P and my effect size and all that. So what I'm going to do right now is just kind of try to get this over so we can see the output. All right. So my T statistic, my T equals 0.68. Degrees of freedom are 7. P-value is 0.521. So if the null hypothesis were true and Derwicky's had this same SAT score, has the population, or the mean difference between the population SAT score and Derwicky Cousins SAT score, right? If that were true, and basically the Derwicky's had an average SAT score, you would find data like ours 52% of the time. P is greater than 0.05. We know nothing. The Derwicky SATs are not different or not the same. We literally know nothing. P is greater than 0.05. When we look at our Cohen's d, we see that the effect size is 0.24. That's basically a small effect. I'm not going to critique you and give you like a p-value like cutoff. I'm calling that a small effect because it's basically a small effect. If we look at the 95% confidence interval of the Cohen's d, we see that the true effect could be a negative effect where Derwicky's are have lower SATs than the average population and have a medium size, or best case scenario, Derwicky's have a large difference between the average population SAT score, essentially confirming that we know nothing, right? The true population effect size could be a medium effect where Derwicky's are not as smart as the average student, or an effect where Derwicky's are a lot smarter than the average student. I need to examine all Derwicky's ever on the SAT. I'm going to have to just keep track of all the cousins' kids and all that and put everybody's score in there. But ultimately, right now, what do we know? P-value is greater than 0.05. This is a small effect. We know nothing, and it's a small effect. Doesn't really matter. Means, standard deviations, medians, all that in your descriptives, no big deal. You're going to use that for your write-up. And your plot is just the 1,000-point marker is right here. Here's the mean. Here's the median. SAT scores. We can see what's going on there. And that's 1 through 3. Interpret our results. Non-significant effect. I know nothing. A small effect size. That's all you have to write. The 95% confidence interval stuff, you could say this shows that this experiment is poor. I have no handle on what the true population effect size is. Could be a medium effect where Dirichis are not smart, could be a large effect where Dirichis are smart, or could be anything in between, right? But you don't have to write about that. That's just me being me. I want you to know that that exists. Okay. So then the write-up, we'll get to that next. What do we know? We know a one-sample t-test indicated that the Dirichis SAT scores, means and standard deviations presented to 2 decimal places, means and standard deviations italicized, were not significantly different from the national average of 1,000, and the observed difference was considered small. T with 7 degrees of freedom equals 0.68. There's a 0 in front of that because T values can be much larger than 1. P, on the other hand, italicized P, equals 0.521. That one, you don't need the 0 in front of it because p-values, the largest p-value you can have is a 1, so you don't need the 0 in front of that. Your D, comma, your Cohen's D is 0.24. Again, you do need the 0 because you have Cohen's D's that are much larger than 1. Finally, the 95% confidence interval is included, and it shows us that in this case, we really know nothing. So the first problem we're going to work on together is an independent samples t-test. It's an independent samples t-test because this is a true between subjects design experiment. Between subjects designs, you can tell them because each participant only gives you one dependent variable response, okay? In this case, participants were randomly assigned to these conditions, but people could be naturally assigned to conditions as well. That's just what they bring with them to the experiment. Nonetheless, what I've done is I've copied and I pasted the data into Jamovi, and now I'm going to show you what I need to do next. I'm going to change the variable name to participant. I'm going to change the type to an ID type. I'm going to change the next variable name to condition, and I'm going to leave it to nominal type. And my last one, my dependent variable is happiness. I'm going to change that to a continuous variable. My dependent variables are always continuous. Now the analysis is pretty straightforward. Click Analysis at the top, click T-Test, click Independent Samples T-Test. My dependent variable is happiness. My independent variable is my grouping variable, is my condition. All I need to do now is click the right boxes. I would like my effect size. I would like my descriptives. I would like my descriptive plots. Let's make this the focus of our output. First question, we find our p-value, 0.317, right? P-value and effect size, right? 0.317, and the effect size is negative 0.77. The p-value suggests that if the null hypothesis were true and these two population means were identical, we would find data like this 31.7% of the time. This is greater than 5% of the time. We retain our null and we state we know nothing. We do have a large effect. And you're probably like, okay, large effect there, okay. We'll deal with that in a second. These are descriptives. You'll need those for your reporting. But if you look at our plots, what do we see? The experimental condition is happier than our control condition. All right. Now, I was talking about 95% confidence intervals. They are optional, but you just click one button and you get them, okay? In this case, you can see why when P is greater than 0.05, you know nothing. The true population Cohen's D is somewhere between a negative large Cohen's D and a positive large Cohen's D. What does that mean? Well, the effect size for our data for this comparison is negative, and it's negative because the experimental group is larger than the control group, and the control group is first, so it's just a negative subtraction. 2.25 minus 3.50 is negative. So that's why the T statistic is negative, the effect size here is negative, and this negative effect size is saying a large effect where the experimental group is happier than the control group. So that is the limit of one of your effect size, is that the experimental group is happier than the control group. The other limit is the flipped effect size, and that suggests the control group is happier than the experimental group. That is also a large effect. So the true effect is anything between a large effect where the experimental group is happier than the control group, right here, everything in between, and it ends at an effect size where the control group is massively happier than the experimental group. So it could be a large effect where the control group's happier than the experimental group, a medium effect where control is happier than experimental, or a small effect, control is happier than experimental. Null. A small effect where the experimental is happier than the control, medium effect where the experimental is happier than the control, and a large effect where the experimental is happier than the control. We literally know nothing. That's how you process this data. When we are reporting our output, we simply write an independent samples t-test indicating that participants in the experimental condition, means and standard deviations, M and SD are italicized, were not significantly happier, so I'm referring to the p-value there, than participants in the control condition, M and standard deviation for the control condition, mean and standard deviation italicized. But the observed difference was considered large. That's a nod to the effect size. T with 3 degrees of freedom, you'll see that in the output, df, degrees of freedom, equals 1.09. Your p-value equals 0.317. The Cohen's d is large, but the 95% confidence interval of the Cohen's d suggests that the true effect could be anything from a large effect, where those in the control condition are happier than those in the experimental condition, to a large effect where those in the experimental condition are happier than those in the control condition. It could be any effect size that falls in between those two large and opposite effect sizes. So we literally know nothing. And that's what I mean when we say our p-value is greater than 0.05. We literally know nothing at the end of the day. So one thing you'll notice that I did that was a little weird was I changed the signs on my T and all my Cohen's D. And that's because the subtraction that Jamovi did was the opposite of the subtraction that I would have done. But that's okay. When that happens, you just change the signs. Now, ultimately, for me, a positive T statistic indicates that the results were in line with my hypothesis. So I predicted that the experimental group would be happier than the control group. That's why I changed the sign on the T. If I change the sign on the T, I also have to change the sign on the D. And that positive Cohen's D indicates that the effect is in line with my hypothesis. The negative Cohen's D, once you follow this formula, or this algorithm, or whatever you want to call it, that negative Cohen's d for me means that the effect is opposite of what I predicted. So looking at that 95% confidence interval again, this could be a large effect that's the opposite from what I predicted to a massively large effect in line with what I predicted. And it could be anything in between those two, any effect in between those two. My true population effect size, I have no handle on what that could be. So this is how you write it up. So now we have a second problem. It's a dependent samples t-test. How do I know when something's a dependent samples t-test? It has a within subjects design. There are two other names for dependent samples t-tests. So synonym toast crunch here, okay? Dependent samples t-test, pair samples t-test, repeated measures t-test. They're all the same thing. They're synonyms, okay? I'm going to call it dependent samples to contrast it with independent samples. Now, essentially, here we have the same participant completing a happiness measure twice, once in the control condition, once in the experimental condition. So we have 4 participants who each gave us 2 measures of happiness. Whenever a participant gives you more than one measure of your dependent variable, you know it's a within subjects design. There are 2 other cases when you use the dependent samples t-test. I like to say, number 1, twin studies. Okay, if you have 2 twins, one's randomly assigned to the happiness condition, one's randomly assigned to the, one's randomly assigned to the control condition, one's randomly assigned to the experimental condition, then you would use a paired samples design. Also, if you pretest people for a third variable, so if you're like, oh, I'm worried about anxiety, so I'm gonna pretest all my participants on anxiety and just choose matched pairs of participants that have the same exact level of anxiety. You would analyze that data with a dependent samples t-test as well. Now, the reason being is that your data are not independent of each other. Twins are related, their data is related. Matched pairs are chosen specifically because some aspect of their data is related. If you don't understand that, ask questions in class, but this is a simple problem. This is the common case. This is 98% of the time. You have the same participant giving you 2 measures under 2 different conditions. So 2 happiness measures, one in the control condition, one in the experimental condition. I have copied and pasted my data into Jamovi. You can enter it by hand as well. I am going to make sure my variables are named correctly. Participant, integer, oh, I'm sorry. It's not a nominal, it's an ID variable. That just tells Jamovi to not treat this like it's data, to treat it like it's an identifier. B is happiness at the control. That is a continuous measure. All dependent variables are continuous in Jamovi. We can make an argument against that, but at least in the designs we commonly use in psychology, majority of the time, your dependent variable will be a continuous variable in Jamovi. This is now happiness at experimental. This is continuous as well. So now we have our data set up. Let's do our analysis. T-test, paired samples. Remember, dependent samples, repeated measures, and paired samples are all synonyms for each other. I hate it too, but that's just how it is. Paired samples, t-test, it's like asking for paired variables. I click my paired variables in. I would like my effect size. I would like my descriptives. I would like my descriptive plots. I no longer need the original data. Let's make this nice and big for us. We have all of our, I'm going to hide this so we can see our output a little bit better. So currently, this is the bare bones of what you need. Again, it's the same data, just entered as a, within subjects design. We can see that the happiness at experimental group and happiness at control group, they're, you know, the happiness over there. We can see that the experimental group, even though it's a little kind of cramped down here, this is the experimental group, is happier than the control group. We're seeing that. Now, is it significant? Let's look at our data. So our T statistic is now negative 2.89. Our degrees of freedom are 3. But the p-value, which is what we care about, is saying that the probability of sampling data like ours, if the null hypothesis were true and the happiness in the experimental group is the same as the happiness in the control group, we would get data like ours, similar to ours, 6.3% of the time. Now that's closer to our 5% betting decision, right? Our 5% reject the null decision, but it's greater than 5%. What we say here is what we said before. We know nothing. So our p-value is non-significant. It's greater than 0.05. We know nothing. The effect size appears to be massive. And right, like some folks are like, oh, it's almost significant and it's a large effect size. Let me show you why I care about the confidence interval. I plug that in here, and what we see is that we see our 95% confidence interval of Cohen's d. And you know, the negative effect size is going in the direction of what we found, and so that's experimentals greater than control. So we see that the true population Cohen's d could be a massive effect where those in the experimental condition are happier than those in the control. Or it could be a tiny effect in the opposite direction where those in the control condition are happier than those in the experimental condition. We don't know where the true population value lies, so we have to assume to some degree that it very well could be that small effect where those in the control condition are happier than those in the experimental condition. It could be a null effect as well. It could be a small effect where those in the experimental condition are happier than those in the control condition. Could be a medium effect where those in the experimental condition are happier than the control condition. Could be a large effect where those in the experimental condition are happier than those in the control condition. We literally know nothing with this data. This is a lot of possibilities, and we know nothing. Just like the p-value taught us, we know nothing. So essentially the interpretation here is, yes, p-value is greater than 0.05. The effect size is large, but because the p-value is greater than 0.05, we know nothing. It doesn't matter that that's a large effect size. We can see by doing one extra statistic that we really don't know that much about what that population effect size could be. Right? We don't have, it's not pinpointed. We did a bad experiment. We need to do a better experiment. All right, the write-up is fairly similar. A within subjects t-test, what test did I use, indicated that participants in the experimental condition Means and standard deviation, same rules apply with italics. We're not significantly happier than participants in the control condition. Means and standard deviation, same rules apply with the italics, but the observed difference was considered large. T, 3 degrees of freedom equals 2.89. You'll notice I changed that from a negative because this was actually in line with my hypothesis. Comma, my P equals 0.063, no zero in front of that. My D equals 1.14, but my 95% confidence interval of my D equals a negative 0.07 to a positive 2.87. I changed the signs on the T statistic, on the Cohen's D, on the 95% confidence intervals of the Cohen's D. I changed those signs around. In the parentheses, that is your degrees of freedom. If I didn't mention that on the previous slide, you'll see that is where the data came from. Ultimately, what I do want to point out is that while our p-value is almost what would be considered significant, look at how poorly our estimate is of that true population Cohen's D. It's better than the previous estimate where the p-value was much larger. But still, we don't know if this is a tiny effect where those in the control group are happier than those in the experimental group, or it's anything in between that and a massive effect where those in the experimental group are happier than those in the control group. That's why I like those 95% confidence intervals of Cohen's D, and they are optional. So your homework problem is pretty simple. I would like you to take this data and run an independent samples t-test on this data. That's problem number 1. Number 2, you're going to rearrange the data into a within subjects design and run a within subjects t-test on it, or dependent samples t-test. Ultimately, you're going to assume participant 1 equals participant 1 and 2. So in the second problem, you're going to assume that this is the same person, this is the same person, 5 and 6 are the same person, and 7 and 8 are the same person. So ultimately, you're going to want to run 2 t-tests and report them out. Now, when you report them out, I'm going to show you how to solve these problems in a second. I'm not going to show you how to solve the reporting out problems because I've already done that. You're going to have access to my slides. You can download them you'll see it on my website. You can download the slides from the website, copy and paste my answers into a Word document. Copy and paste everything into a Word document with all your answers in there, and ultimately change the write-up so that it fits your problem. And don't lose these write-ups. They're pretty good. They're not perfect, but they're pretty good, and they'll be useful to you while you write your final papers for lab and so forth. Try to do this. Pause the video. The answer is next. All right, let's run this homework. It says first run this data set like it were an independent samples t-test. It's set up like an independent samples t-test. So I'm going to go ahead and copy and paste my data into Jamovi. Now I have to fix my variable types. This is participant. It's an ID type. This is my condition. This is a nominal type. And this is my happiness scores, and this is a continuous type. All right, so now I go ahead and I'm like, well, let's run my t-test. T-test, independent samples t-test. My dependent variable is happiness. My grouping variable is condition. I need to just click my effect size and my descriptives and my descriptive plots. I'm going to hide that. I also would like my 95% confidence interval, but I'm going to click that in a second. I'm going to go ahead and make this big. I no longer need that data file at all. So we can see here, what do we see is going on? We see that the experimental condition appears to be happier than the control condition. We see that our p-value appears to be 0.028, and our effect size appears to be rather large. When I go ahead and click my confidence interval, we learn something very important here. So while this is a significant effect, right? Significant and large effect, where the experimental condition is happier than the control condition. Degrees of freedom are 6, you'll need that. T statistics right there. We see that the true population effect size could be anything from a large effect where the experimental condition is greater than the control condition to a tiny, tiny effect where the control condition is happier than the experimental condition. In general, when your p is less than 0.05, you don't find this. However, sometimes you do, particularly in smaller sample sizes like this study. But what it's telling me, this tells me that the true population effect size could be a tiny effect against my hypothesis where the control group is happier than the experimental group, or a massive, anything between that and a massive effect where the experimental group is happier than the control group at the population level. Ultimately, this is a case where it suggests I need to run a better study. Now, you didn't have to do that. Under the traditional rules, this is a significant and large effect. It does matter. However, when I added this extra statistic, it added an extra piece of information that makes me say, hey, I should really increase my sample size in this data set. I only have 4 participants. I should get a lot more than 4. I'm sorry, I only have 8 participants. I should get a lot more than 8 participants. Okay. When you write it up, you can choose to put in your statistics exactly as they are shown, or you can choose to flip the signs on your statistics. These all become positive and this becomes negative. The choice is yours. What matters is that you understand that the experimental group was significantly happier than the control group, and that means in terms of the population. We are inferring that the population happiness of people in the experimental condition is greater than the population happiness of those in the control group. But essentially, that's what we know. So now I'm going to go back to the data, and I'm going to rearrange it just so that it is a within subjects design. So participant 1 and 2 is actually one participant with a score of 1 and 2. Participant 3 and 4 is actually one participant with a score of 3 and 4. Participant 5 and 6 is actually the same participant. I'm assuming that based on the instructions of the data. One and five. And so now I'm going to go ahead and run the same data as if it were a within subjects design. First thing I need to do is I need to delete these 4 rows. They're no longer part of my data. I also need to delete these 2 columns. They are no longer part of my data. But now my data is almost set up, right? That was my old analysis. I'm just going to remove that. I need to make sure that my dependent variables are named correctly and they are continuous. This is happiness at control. And this is happiness at experimental. Those are both continuous because they are dependent variables. Now I've converted the data set from an 8-participant data set with a between subjects design to a 4-participant data set with a within subjects design following my rules as stated in the PowerPoint slide. Now, ultimately, let's run our analyses here. It's not going to be too bad. T-test, paired samples. Click in my variables, both of them. You can click in one at a time and then click in the second one. You can see that we are getting this p-value right here. Let's go ahead and click our effect size. Let's just interpret this as we would without the confidence interval. We also need our descriptives and our descriptive plots just for the write-up. The plot helps us see that the experimental condition is happier than the control condition. I haven't changed that property throughout this lecture, so that shouldn't be a surprise, but you always want to look at your graph first. Our p-value states that if the null hypothesis were true and the happiness of the population happiness of everyone in the world in the control condition equals the population happiness of everyone in the world in the experimental condition, we would obtain data like ours only 6.3% of the time. However, that's greater than 5%. We didn't cross our betting threshold. We retained the null hypothesis. We know nothing. You look at that effect size, that's a large effect, but remember, p is greater than 0.05. We know nothing. It doesn't matter if that effect is large. Now, when you click that confidence interval, we see something very similar to what we saw in the previous analysis, and that is that essentially the true population effect size could be a large effect size in the direction that we found, where the experimental group is happier than the control group. That's what this negative 2.87 means. Or it could be a tiny effect in the opposite direction. The sign switched from negative to positive, so that suggests it could be a tiny effect where those in the control condition are happier than those in the experimental condition. What does this mean? It means I know nothing, right? I know nothing. The effect, could be anything, any effect size between large, where the experimental condition is happier than control, and anything between that and small, where the control is happier than the experimental condition. It could be anything in there, including null, including, a small effect in where the experimental condition is happier than the control condition, a medium effect in that same direction, and so forth. You can look at that and say, we literally know nothing here. P is greater than 0.05, we know nothing. That still holds true. I will allow you to just do the write-ups. I'm not going to show you how to do the write-ups. I've already shown you how to do write-ups. The one thing I do want to say is that you can include, this negative t statistics, and you can include it exactly like it is here. I just personally would change my t statistic to positive. My degrees of freedom are 3, note that. This effect size to positive, this effect size to positive, while this one changes to negative, because I like positive t statistics and positive effect sizes to be in line with my hypothesis. In this case, I set up the data so that the experimental condition would be happier than the control condition. I can see that that is true from my graph down here, which is just the two means, and we can see that. Now, you can't see on the bottom. That's just a little ugly, but that's what's going on. You can see it here if you're a little confused. 1.54, so forth. But we can see that. And ultimately, when I write up my results for publication, that's how I write them up, so that positive effects are in line with the hypothesis and negative ones are against it. But, it's a choice. It's up to you. No one's going to reject it for that reason. So I hope that makes sense. That's how you do your homework. I'm not going to show you how you do the write-up, but essentially take my write-ups from my PowerPoint, copy them, paste them, change the wordings and interpretations to match. In this case, I know nothing, even though the effect was large, essentially. Non-significant, I know nothing, the effect was large. I do add extra stuff. The 95% confidence interval thing is optional. If you don't understand it, I'm just going to give it one more shot. In this case, the true population effect size could be anything from a negative 2.87 to a positive 0.07. Right? Anything in between those two effect sizes. It switches signs, nulls included. It could be that the two means are the same. Could be that there's a massive difference where those in the experimental condition are happier than those in the control condition. Could be a small effect where those in the control condition are happier than those in the experimental condition. You can see that I literally know nothing in this example as well.